Well, hello there. This is Craig Hane, or Dr. Dell to my students, and this is going to be a video on calculus that I promised you. And so let's talk about just what calculus is really all about. Of course, as I've already said, you are assumed to have been through tiers 3 and 4 of my math program, and in particular, Dr. Simmons' book. And so that's got to be the background for this program. Well, here is the situation. Suppose you have a function, and I will just draw the graph of it, and I'll start with a very simple function. Let's say you have a straight line, and you all know then if this is the x-axis and this is the y-axis, that the equation for this function would be y equals mx plus b, where m is what we call the slope of the function, and that means that if you start a point here and go out to here, and we call that the run, and then if you go up to here, and that's called the rise, then the slope is just the rise divided by the run. Now, by definition, the derivative of this function is going to be, by definition, at any given point is going to be the slope. And since that's the same everywhere, the derivative of this is going to be a straight line where this is the height m. And this will be called the original function. I'm going to call this f of x, and this will be called f prime of x for the derivative of x. And that's the definition of derivative for a straight line. And you really don't need algebra, or pardon me, you don't need calculus to understand this. We handled this type of thing in the tiers 3 and 4, actually in tier 3, and we didn't use the terminology of derivative. We just called this the slope. But f prime of x equals m for this example. Now, the problem you get into in mathematics, of course, is that usually you do not have, or many times you do not have straight line functions. Suppose you have a function like this, and suppose it's a curve function. Now this is the x-axis and this is the y-axis, and the notation we learned was y equals f of x. That's the standard notation, and f kind of stands for the word function, but you can use any lever here. You can have y equals g of x, or y equals beta of x, or whatever. And what's understood here is if you take any particular point in the domain of the function, that is on this x-axis, which is called the domain, as you recall, and call that point A, then if you come up here on the graph of the function, this is a f of a. So this is the point. If you come over to here, this is f of a. It's that height there, okay? Now, this is something, of course, we learned about in basic, the basic pre-calculus mathematics that you've already studied. Now the question is, could you meaningfully define the slope of this curve line in any way? When we had a straight line, we knew what we meant by the slope. We meant the rise divided by the run. And of course, it didn't matter where you were on the straight line. That was always the same because of similar triangles. We learned all about that in the pre-calculus. But now, it's clear that if you move along this curve, the slope is somehow changing if you can figure out what it would mean. What would it reasonably mean? Well, what our ancestors decided, and it's a very reasonable thing, is to imagine that at this point you've got a tangent line. Okay, I'll call that, what should we call that? TA of x. That means this is the tangent line. Well, that line has a slope. I'll call it m sub a, and it has the equation then, t of ax equals m sub ax plus b, where b is going to be the y-intercept that we've learned about back in pre-calculus. So this would be the reasonable definition of slope. So we define the derivative of f at a, and we use the notation f prime of a, and this is called the derivative of f at a, or maybe I should say f at a, and we define that to be now just this ma. This is a definition. The derivative of the function f at the point A is just the slope of the tangent line. That's all there is to that. You understand that? Do you see? Now, what would happen if we moved over here and took another point? Say we moved over to here and we took a point B. Well, it would have a tangent line here. That would be the tangent line there. And that would be T of B. And so then f prime of B would be the slope of that tangent line, which would be a different slope because it's a different straight line. It has a different rise and a run. So that's really the definition of derivative. Now let's see how we might go about computing a derivative in some calculating way. Suppose you have, again, a curve. I'll just draw a curve like this time. And suppose we have a point A here, and this is the point. This is f of A. Well, the tangent line comes along here. And what we could do is now I'm going to blow this up. We could come out here some small distance, and we'll call this distance dx. This is the x-axis. So dx is intended to denote a very small amount of x. So this would be the point A plus dx. And then if you come up here, this would be the rise of the tangent line, and that's almost the same as the rise of the function. They're very close to each other. And so we're going to actually then consider this as the rise, and this would be f of A plus dx. That's this height minus f of A, and that would be the rise. And the run is what? Well, you've gone from A to A plus dx, so the run is dx. So if you take the rise and divide it by the run, this is equal, then this would be the derivative. So f prime of A can be thought of as then f of A plus dx minus f of A divided by dx, assuming that dx is essentially 0, very, very small. Now, this is an intuitive definition, and it's easy to take a calculator and calculate derivatives now for specific functions. But of course, to make all of this completely rigorous, so this equal sign, it does take some mathematical machinery, which we do discuss in the calculus course that we give you. But this is the intuitive idea, is you take the run and you take the rise. Now, technically, you only ought to go up to the tangent line. But if this was dx was really very, very small, then this tangent line would be very, very close to this height here. And so this rise that I've indicated here would be essentially the rise of the tangent line. And that's why this whole definition works. Now, what we do in our calculus course in Tier 5 is we then take a bunch of actual problems and we actually calculate this for a bunch of things. And it's not very hard to do thanks to a calculator. But the next thing that you really need to think about is this. We have a function y equals f of x, and for each point on that function, we define a derivative. So like right here, the derivative looks like it's a little bit positive. And then as you move over, the derivative is a little bit less positive. It's still positive, but it's a smaller number, right? You see the slope's bigger, then it gets smaller. So the derivative is going down. And in fact, when you get all the way over to this peak here, the slope would be 0. You'd be down to a 0 derivative. And as you're coming back this way, the derivative is higher. So what we actually have here is we have now a new curve, and this is called the derivative function. And what it means is that at any point A, this of course is, the height is f of A. At that same point A, this height is f prime of A. Whatever the slope up here was, that determines this height. And if this function were going down, so you had a negative slope, then you would have a negative derivative. So that's what would happen to the derivative curve. So anytime you have a function f of x, you have a derivative function. So you started out with what's called a local definition, because we only talk about defining the derivative at a point, and that's called local. And then we expand that to a global definition by saying, okay, if you have a function, you can define its derivative at all these points, and that in turn then defines a new function called the derivative function. So now let's summarize what we've got. We have got, in general, a function that will have a graph of some sort, and we call this y equals f of x. This is the x-axis, this is the y-axis. And then from that, we can calculate a derivative function called y equals f prime of x. Now we can do it, we can almost eyeball it if we want to. For example, here we have the derivative is some positive number, and then as we move over to about here, the derivative is getting smaller and smaller till it gets to 0. So I'll just kind of line that up. That goes down to there. And then here it kind of stayed around 0, got a little bit negative, and then it started positive again. So something like that. Now, the real challenge then in calculus is, given a derivative function, how can you evaluate or figure out what is its, given a function, how can you calculate what is its derivative function? That's kind of the challenge then of calculus, of differential calculus. And so what we do in differential calculus is we actually begin to, in essence, create a table of derivatives. We start out, for example, and we say, well, suppose that the function is a straight line. Then we've learned that its derivative function is just a constant. That's the slope of that straight line. So this is f of x always up here, and this is f prime of x. And then we ask ourselves, what if you have a function, let's say it's a parabola, x squared. Well, it turns out we can calculate that its derivative function is a straight line. And what if you have a function, so if this is x squared, f of x equals x squared, this is f of x equals 2x is its derivative. What if you have a sine function? Now this is kind of interesting. Let's just take a quick look at this. At the origin, this slope would appear to be about 1, so we'd start at 1. And as we move over to here, this is 90 degrees. It looks like the slope is getting smaller down to 0, and it turns out it looks like that. And then we'll go more negative, negative till we get to minus 1. And so we get to here, we go to there. Now, if you remember your trigonometry from tier 3 and 4, this is the sine function, sine of x. This looks like the cosine function. And so you might think that if f of x is, and by the way, there's an alternative notation. If this is f of x, f prime of x is sometimes called d of f of x. And so you might think that the derivative of the sine function is the cosine function. And as a matter of fact, that's exactly what it turns out to be. So you spend a good deal of effort in the first part of calculus in creating a table of derivatives. Another example would be if this is the natural log function, ln of x, then its derivative function is the hyperbola 1 over x, believe it or not. And another example would be if this is the exponential function e to the x, its derivative is, in matter of fact, itself. It's its own function. In fact, that's the only function that is its own derivative, is e to the x. And so you go through and you create a catalog. And then you learn how to combine functions and do derivatives of them. For example, you learn that if you have two functions, f and g, and you want to know what is their derivative, it turns out that it's the derivative of f of x plus the derivative of g of x. So that would be one of the first rules you would learn. You might say, well, what is the derivative of the product of two functions? And you might think, well, it's just the f prime, derivative of f times the derivative of g. You might think that. In fact, that would be a very reasonable first guess. It turns out A couple quick examples, you'd find out that is not what it is at all. It's wrong. Well, what is it? Well, it turns out that it's f prime of x times g of x plus f of x times g prime of x. This was discovered by our ancestors back in the 1600s, and this is called the Leibniz rule, after one of the inventors of calculus, Gottfried Leibniz. You might take the composition of two functions. You might take a function f and plug into it g of x, and then you say, what's the derivative of this whole thing? Well, it turns out it's the derivative of f evaluated at g of x times the derivative of g of x. And this is called the chain rule. And this is something you learn in the very beginnings of differential calculus. And with these things here, you can now create a very extensive catalog of derivatives. It's very easy to do. Now, it turns out there's also some other terminology here. We said that if we have f of x up here, the f prime of x is the derivative of f of x. We can also go the other direction, and we can say that f of x is the antiderivative of f prime of x. So this catalog can actually work in both ways. If I ask you, for example, what is the antiderivative of 2x, since you can find in this catalog the function whose derivative is 2x, namely x squared, then you would say, well, the antiderivative of x squared is 2x. And in fact, that's given a notation. If you take this symbol here, this Greek summation symbol times f prime of x, that's called the antiderivative. So that's another notation that you're introduced to, another definition and notation. Now, the other thing that we do in the beginning calculus class is we find applications of now derivative. Derivative is a rate of change. After all, what we're talking about when we talk about slopes is we're talking about how rapidly is this increasing or is it decreasing. So really, the concept of derivative is all about rate of change. And of course, then this has many, many applications. So you go through, as you're learning to use derivatives, you start studying examples from physics and, let's see, physics. I have to slow down when I spell here when I'm talking. Chemistry, economics, any kind of a science subject or a social science subject, you always have rate of changes. And there's some more notation that you'll run into. If this is y equals f of x, I told you that the derivative is f prime of x, and that is also sometimes denoted dy by dx. And the reason for that is pretty clear if you remember the definition of derivative. You have a function here, and you start at a point, and if you go out dx, and then this would be considered dy. You're just taking the rise divided by the run, dy over dx. Of course, this is kind of an abuse of notation, and you've got to be careful you understand what this means. A better notation for this would be, and the reason it's abusive notation is this x and this x are not the same thing. This dx represents a very small number, and dy is a small number, and then this is their ratio. So a better way to write this would be f prime of a equals dy dx evaluated at x equals a. That would actually be a better, a more precise definition, and indeed it is sometimes given, but then it's always abbreviated to this, because what we do in mathematics is what we call abus de langage. We abuse the language. We take our notation and we sometimes make it mean different things, and you've been learning about that in the tiers 3 and 4, of course. So this is the basic idea then behind differential calculus. It's pretty simple. You simply, in essence, you do two things. You create a table of derivatives. So you have a function here in this table, and below it you have its derivative function. And we've already seen a lot of them. For example, the derivative of the cosine you would learn is minus the sine. And we talked about some of the others that you would have. And you have a whole table. And if you go backwards, so coming down, you're talking about the derivative. And if we come up the other way, we're talking about the antiderivative. It's just terminology here. That means we're using the table backwards. It's kind of like logs and antilogs, if you knew about that. So the cosine could be considered the antiderivative of minus the sine. Just like the derivative of the cosine is minus the sine. And by the way, if you weren't sure about that, all you have to do is look at the graphs to convince yourself of this. It becomes very quick and easy. Then you learn to apply this to various scientific and engineering subjects, and it turns out this is really the basis then of a lot of modern science and engineering. But it's not enough. The real problem now comes in, and in fact, one more thing I want to tell you before we depart this particular video on differential calculus, and it's the following thing. How do you suppose that if you're down here and you've got a function, I'll call it g of x, how do you suppose you can find the antiderivative? Well, it turns out this is not easy to do. And that's what I'm going to really tell you a secret to in the next video. It turns out that there is another operation in calculus, and I've told you about it earlier. There's another type of calculus called integral calculus. And it turns out this is kind of, in some sense of the word, the reciprocal or the inverse of differential calculus in a very clever way. And I'm going to teach you that in the next video. And that's when calculus has become, this is just integral. That is when calculus has become extremely important in modern science, starting in about the 1600s with the discoveries of Isaac Newton. So we'll talk about that in the next video. But for now, you should have a pretty good idea of what the derivatives are in differential calculus. So this is Dr. Dell. I'll see you in the next video where we'll talk about the integral calculus.